Hi there, it's exercise 21D for year 13 maths students. Equilibrium of forces. This is where forces end up being equal to each other, I suppose is the best way of describing it. But forces aren't necessarily acting all in the same direction. So for instance here, I've got these 5 forces all acting on a point in the middle. And probably the best way to determine whether or not they are in equilibrium is to think of each force acting followed by the other. So rather than this picture where, and this is the right picture, this is one thing happening, one particle in the middle and 5 things happening to it. But rather than that, I'm going to just do it slightly differently. And I've just drawn this in sort of light transparent version. It's exactly the same this. But what I want us to imagine is we're going to do this force first. So simply because it says A and no other reason. So I pick one force and basically do what it says. But then it says do B. And B kind of goes up here. But I'm not going to think of it there. I'm just going to do the equivalent. So rather than drawing that force going that way from the end of A, I'm going to try and draw it there instead, which must be about there. So therefore we've done the A, we've done the B. And what does C look like? Well, C goes off in this direction. Again, I need to try and get the angle right, and I need to try and get the distance right. About there. It's hard. You can appreciate it's a bit hard to do. Now D brings it this way. Again, angle-wise, something like that. Who doesn't really know? Something like that. D. And of course, you could do it really accurately. And E then kind of brings it back home. That's my E. And to be honest, it's much better thinking of it like this. We started off with 5 forces. This is 5. You can see the overall, assuming I draw that accurately, they come back to the start. And because they come back to the start, these forces A, B, C, D, and E would be thought of as being in equilibrium. That's the idea, at least. Now, sometimes they say to you that the forces will be in equilibrium, sometimes they don't. So let's just read a few questions. Starter. A force of 5 newtons acts on a particle of mass 2 kilograms. Well, this looks like suvat, doesn't it? So I'm just going to write in this space here, I'm going to write suvat, and I'm going to then see if I've got. It says if the particle is initially at rest, after how many seconds will its displacement be equal to 5 meters? And of course I haven't got enough information. I'm missing either a V or an A. But of course that doesn't matter because I can actually get the A from this. Look, a force of 5 newtons acts on a particle of mass 2 kilograms. This of course is F equals ma. So 5 newtons equals the mass times the acceleration. My acceleration must be 2.5. So that's now 2.5. Which equation is it? It's SC equals UT plus a half AT squared. It's one of those ones which without a calculator pain because you've got to solve a quadratic equation, but well, it may have to. Actually, maybe not. Let's write this in. 5 equals, probably not actually because 0 times t is 0, so that effectively goes. A half of A is 1.25 t squared. That's not too bad at all, is it? Move the 1.25 over. 5 divided by that is 4 is t squared. So t is plus or minus 2. I'm going to assume it's positive, otherwise it doesn't really make much sense. So 2 seconds is my answer. 2 seconds is the answer. Check for perpendicular forces. I've given myself a little clue here. A particle weight 80 newtons is attached to 2 light inextensible strings, which are also attached to a horizontal ceiling. Okay, there are the strings are perpendicular to each other. Are you right? So the strings are perpendicular to each other. I assume this is one string then. And that's, I don't know which one to call that. This is another string. Let's call the left hand one T1. That might make sense. And the right hand one T2. The strings are perpendicular to each other and make an angle of 35 and 55 to this ceiling. And I suppose because of alternate angles and stuff, I can assume that this angle is alternate to this. This is 35 and this one is 55 degrees. Yeah, that makes sense. Find a tension in each string. Well, I suppose one thing we can do is resolve says check for perpendicular forces. I suppose that's a hint that you can do this in more than one way. But I'm just going to go with this technique, which let's just show you the technique and then we'll decide at the end if it's the best technique. So I'm going to try to resolve them so that they are. So I'm going to look left and right first of all, and I'm going to see what force are acting. Now remember, this is all, it implies that this is in equilibrium. It doesn't say this magic word, but it says it's attached, it's not falling down. This is all set up so that it just sits there, so they're in equilibrium. So I reckon forces left equal forces right. Now I'm going to resolve the T1. I'm going to write T1, and when I resolve it in this direction, I think that would be cos 35, and I think that's got to be equal to the force to the right, which is T2 cos 55. Now, it's not the easiest way necessarily to do it, but I quite like this method, because if you do it this way, it's the same every time. If I do it this way, and I might show you this in a bit, it's actually quicker, but maybe harder to grasp what's going on. So anyway, you resolve left and right, cos goes across. So therefore, if I do it upwards, it'll be sines. So forces up will be T1, this is going upwards now, T1 sine 35. Plus the T2 sine 55 is equal to the force going down, which is 80. Now, definitely it's the case that probably I could do this easier, but I'm going to go with this. So T1, I'm going to set this T1 equals to T2, and you'll notice that moves over, and I get T2 cos 55 divided by the cos 35. And I can actually work that out, cos 55 divided by cos 35. It won't be the prettiest method of doing it, but it will perhaps be more understandable. So cos 55 divided by cos 35, and I'm going to need a few decimal places. I'm going to use this cheaty method. It's 0.70020. I'm going to write 8. It's not exact, but I have lots of decimal places. I'm not going to lose any accuracy because I've got lots of accuracy there, times by the T2. So that effectively I've worked this bit out. Why have I done that? Because where it says T1 now, I can replace it with this. So I've got I've got way more, too much accuracy, 0.700208 T2. So I'll get rid of this and I'll write that. Don't forget to times by the sine 35 plus T2 sine 55. And if you like, one way of doing this is to take out T2 as a common factor and do this times by the sine 35 plus the sine 55 equals, don't forget that all this is meant to be equal to 80. So if I just set that equal to 80, I can just do what was on my screen, times by sine 35 plus sine 55. What do I get? I get 1.22. So 1.2208 T2 equals 80. So I think I can just divide one by the other. 80 divided by that answer, I get 65.5 newtons. And of course I've got this formula now for working out T1. T1 is this decimal times what I just got. So I can just times it by 0.700208. I get 45.9 newtons. There, right? Yeah, I'll just check the textbook and they look right. Now, in fact, I've got them here. Yes, I do. Now, what's interesting about that, I suppose, is it's not necessarily the easiest method. But I'm going to try it and do it just like that. And perhaps in class, I'll show you this alternate way of calculating that using what I've called up here, perpendicular forces. Another example then, particle mass 4 is attached to a cylinder. This looks ridiculously simple, in as much that it's the same as last time, surely. Given that the particle is in equilibrium, find the magnitude. It's the same question, just with different numbers. It's 4 kilogram force now, so I suppose I've got to do, the weight is 4 times by 9.8, which is 39.2. But I'm going to do it the same way. I'll do it left and right. So remember what we did. We said 30 degrees there, 30 degrees here, alternate angles. And we're going to resolve. That's 35. So I'm going to say T1 cos 30 equals T2 cos 35. And therefore I can write T1 equals T2 times by, and I'm just going to do that cos 35, cos 30, cos 35, close bracket, divided by cos 30, 0.94. And again, I'm going to write it to a few decimal places, 588. So I've now got that. Going up and down, remember we're resolving upward now, and both of these resolve upwards. So we've got T1 sine 30 plus T2 sine 35, and that is equal to 39.2. But I'm going to write that here instead. So where it's got is T1. Now I've also got times by sine 30, so I'm going to times that by sine 30, which is a half. I'm going to end up here with 0.47294. What's a T2 plus, well, what's sine 35? Well, I might as well just work it out. It's 0.57358 T2, and we don't have to be perfect with this as long as we've got enough. If it was an algebraic exercise, perhaps I'd care a bit more. So I'm going to add those together, 0.47294. And I get 1.0465 lots of T2 equals 39.2. So if I do 39.2 divided by that answer, I get T2 equal to 37.5 newtons. I stress it's not the only way of doing it, but it's not a bad way. T1, of course, again, I just need to times my answer by that. Times by 0.94588. T1 equals 35.4 newtons. No idea if they're right. Yes, they are. Again, it's not necessarily the only way of doing it. Three forces act on a part or new example of, say, in a horizontal plane. It doesn't mean that it's flat. It means if we're looking down on it and they're all in the same plane, as shown in the diagram. So given that the particle is in equilibrium, find to the nearest degree the angles between the 10 Newton, it's these two angles here at once. So it may be best to, well, I'm half tempted to split it down the middle. And I'm going to find alpha there, and I'm going to find beta there. But a bit like I did in the right at the beginning, I said that if they're in equilibrium, which these are, we can draw them in a shape, and this might be the best way of doing this one. So I'm going to do this one first. So I'm just going to draw that one, which is 8 long, and that's at an angle, according to me, of beta. And then I'm going to go straight down. And that's 10 newtons long. Doesn't look like it on my picture. And there it's an equilibrium, so I know it joins again. That's 7 newtons. And is that angle alpha there? Yeah. So you notice, effectively, I've made this into a problem, and it's almost like a cosine or a sine rule question. I want to, I can find alpha, I think, using the cosine rule, actually. So cos alpha equals 7 squared. Plus 10 squared. Do you remember the cosine rule? Minus 8 squared. Look it up. This is the rule for finding the angle. Divided by 2 times 7 times 10. So if I type this in, 7 squared is 49 plus 100 minus 81. To the top I know divided by 2 times 7 times 10. I get 17 over 35. So alpha then is the inverse cos of 17 over 35. The inverse cos of the answer equals, I get 60.94 degrees. Now I don't think I've got time to finish this question, but obviously my job now is to work out beta, so presumably I can use the sine rule to work out this, maybe, yeah, and then somehow, or is it, do I do it from up here? I do it from up here, find this angle, and these will be alternate. I'll finish this in class. Notice the 60.94 isn't what they asked for. I found beta, so I've still got a bit of work to do. Well, not much work to do to find that. But in class then we will have a look at exercise 21D. Okay, thank you very much.